But we're doing wristbands to get everyone in. The wristbands are going to be available at the registration desk at 6:50, just prior to the last talk of the day. You get a wristband that gets yourself in the door, and then you get a business card that you exchange at the front door for drink tickets. And there you get your drinks taken care of. So you'll need both the wristband to get in and the business cards to get your drink tickets going. So, and once again, 6:50 before the last talk, registration desk. And right now we got a longtime friend of Toorcon. Dan was just saying, 6 years, 7 years now? 6 years. And he's up here to obviously do everything he possibly can over DNS and to drink as much as he possibly can. I think this is the first time that Dan's actually been on a Toorcon stage, either not drunk or hungover, so something's horribly, horribly wrong with the universe. So someone help this man out. But Dan Kaminsky, everyone, let's give him a big round of applause.
What's up, guys? Yo. I love this con. So, not really what the whole talk's about, but last year I talked about pretty pictures from data and code and software, and I kind of ported it all to Winamp. It wasn't supposed to be useful, it was just supposed to be all pretty. And then I started throwing it at audio captions. You know, like you hear 1, 3, 5, 5. And it turns out this thing that was just for fun and cool and neat, it kind of actually shows you, oh hey look, here's the number repeated, and there's a number repeated. So anyone who's interested in that kind of audio processing stuff, come find me later. It's not what this talk is going to be about though. This talk is about midgets over DNS. Damn it, Beetle, that was supposed to be a surprise. No. We're actually going to talk about a new subject that I've kind of avoided year after year after year, which is how do I drink this much beer? So I've gone through a lot of things over the years. You know, I've played with SSH, I've swept networks, I'll do it repeatedly. Billion packets can't be wrong. I've done way too many things with DNS. I really try to avoid it. And I've avoided the web. Because, growing up, San Francisco, late 90s, everyone was doing web stuff. And I'm like, I don't want to mess with the web. It's JavaScript. This is such a crappy language. No, this language is awesome. There's so much crap you can make it do. Seriously, it's not a moon, that's a web browser. About the moment I got the idea, I'm like, oh, me and Photoshop are having some special time right now. but don't worry, Mac fans, you get in too. The best part is I was totally going to Photoshop that scene to look like it was an iPhone, and then I looked at it and I'm like, I don't need to do anything. Sweet. So, the interesting thing about the web is right now it really is where the wild things are. Cross-site scripting and cross-site request forgery is just absolutely rampant. The system was just not designed for the kind of interlinking that goes on right now. The way I explain it to people, the web was designed, bless Tim Berners-Lee's heart, he loves the idea of public content linking to other public content. And that is awesome and great and wonderful in the heart of the web, but people are sticking their private emails on it too. The web was never, ever designed for stuff that I can get there, I can link to it, but you can't. That'd be bad. The whole concept of the web is everything should be able to link to everything. So, fundamental design bugs are failing us. We're getting actually some real issues with image parsers. Last year's Super Bowl had another WMF exploit, unfortunately. 2 days before the Super Bowl, a malicious image was placed on a web page. They got, plus million infections overnight. Those are numbers we haven't seen in some time. What really got me finally to start looking at the web, though, was actually the DNS rebinding attacks that everyone has been researching. I'm just the latest person to go ahead and take a look. Dan Benet's team at Stanford is probably doing the most work. What they actually did, this was great. I've been saying for a while that ad networks that take an ad, take an image, take some HTML, and push them out to thousands and thousands of websites, that these things are have quite some potential for distribution of malicious code. Well, what they did is they actually distributed some malicious code. God, I miss being a student sometimes. No, they actually put a Flash applet for 50 bucks. They got their Flash applet on an ad network for a night. They got into 100,000 different networks. Now, when I say got into 100,000 different networks, it turns out there's this bug involving rebinding in Flash, and you seem to get network access. Okay, so let's take a look here. DNS is involved, tunneling is involved, getting behind firewalls is involved. Okay, I had to take a look. This bug is ancient. This bug goes back to like 1996. It's so old, people forgot about it and put it back. Only design bugs get these kind of screw-ups. It's awesome. So Vinay goes ahead. He's been researching it. Some guys over at Princeton. It was so long ago, we don't even know who the students were. They named it after the university. The whole thing started back up with Martin Johns really reviving it. Arsnake's been pushing it a lot on his blog too. The reason everyone's been talking about it is because it really breaks the security assertions that you can expect from a browser going across the web. To understand how, you have to understand how the web works. Web pages, they are what's called, in the technical term would be late binding. Web pages get a list of things to grab, and they grab them from everywhere. You might get an image from somewhere in Malaysia, you might get some HTML from somewhere in Russia, you might get, you can actually even have, in a web page, a whole second web page. It's called an iframe. It's another window that you can look through, that you can see someone else's page, and it'll load all of its content. And it's all brought together, not at, start, but whatever is around at the time for the browser to grab. This is just how the web works. Now, I told you, you can put websites in. And I also told you that we're very good on the web with being able to handle public content, but what about private content? What if I could put the window into your web page, to my web page, that had Hotmail, and you were logged into Hotmail? Would I be able to now read your email? That would be bad. Well, they thought about it a little. Actually, to be fair, the same origin policy that they created to deal with just this issue of me being able to embed Hotmail and then read your mail, they thought about this quite a bit. And what they created was something called the same origin policy, which can summarize as, look, but don't touch. The idea is you can browse to ioactive.com. You can actually see a window that contains Hotmail, but it can be shown to the user, but the IOActive page can't look inside the frame. Can only generate the user interface, cannot actually programmatically look inside and play. Now the way this security policy works is that it's based on the name. It's based on the fact that ioactive.com is not hotmail.com. And so because of that, you can show it to the user, but you don't get to mess around inside, you don't get to automatically read the mail. The philosophy, the policy statement is, if two things come from the same place though, well then they can look inside. So Hotmail could have an iframe that you could look inside, because Hotmail would be looking inside Hotmail. But IOActive can't look inside Hotmail. Now this seems great, this is very logical, names are great, they're wonderful, and obviously content comes from names, right? No. Content comes from IP addresses. Names don't exist except for on your clients. You use DNS, oh yes, you use DNS to translate between a name to an IP address. The idea was that, IOActive would have its IPs and Hotmail would have its IPs and, never the twain should mix. No, that's not how it works. Any site can return any address it feels like. Foo.com can return its addresses, bar.com can return its addresses, but foo.com can also return bar.com's IPs. And what this means is that the idea of using the name as a summary of the security policy, of saying this content is associated with this name, the problem is that you can get someone else's content and associate it with your name, thus being able to browse inside. So, effects. At one moment, bar.com can point to a server out in Europe. Next moment, no, that's the printer down the hall. Now, suppose your browser loads a page from out in Europe. This, by the way, was a very bad slide to have when I actually was in Europe. They're like, dude, that's down the hall. No, but suppose your browser loads a page from out in Europe, and then it switches over and goes, printer down the hall. Now you have a page at bar.com, and it has another page inside, also at bar.com. But the machine out in Europe has given you a page that's now looking inside your printer and changing settings and redirecting all print jobs to Kazakhstan. As an idea. So, you might say, but, what's the problem? Couldn't the server out in Kazakhstan go ahead and just connect to your printer directly? No. That's why we have corporate firewalls. Lots of people think the firewall is dead. That's because it's working really, really well. That's actually kind of a problem. We've actually started to forget, we used to have a lot worse security when there was no such concept of a DMZ. The corporate model is you have your boxes on your intranet, you have the boxes in the DMZ, and then you have the scary things out there on the internet. This model has been remarkably effective. All those that try to get around it, it's kind of funny when you actually see what people do. They'll put firewalls around individual hosts, they'll use IPsec, but it's still very much of a model of you have the intranet hosts that can talk to each other, you have the DMZ hosts that are very, very locked down. There's very few of them because there's only a few resources that can go both ways. These are the guys that are at risk, and then you have the outside world. That model has that is why all the attacks have gone to the client, because the servers actually gotten locked down pretty well. Unfortunately, what's happening is that we're using the client to get around all these firewalls, and now we can just get to the servers from behind. Crap. So, why the attack works? Browsers don't know that bar.com from the external IP is any different than bar.com from the internal IP. This is totally by design. When you go to Google, you get a list of addresses that you can use. When you go to AOL, you get a list of addresses you can use. And you know what? They all have the same name, and there's multiple IP addresses. You hope that all those addresses are actually owned by Google or Yahoo or AOL or whatever, but you don't know. Yahoo can return Google's IP, Google can return Yahoo's IP. It'll still work, it'll still go, and it'll still be under the same origin. What happened is that for load balancing purposes, we created a dependency on insecure behavior. This sucks. So, the problem is that, you can, first of all, you stop this, you have to detect. We'll talk about stopping this problem later. So what's the canonical attack? Well, the canonical attack is actually getting around a firewall. Again, firewalls are remarkably effective. They've done they've done huge amounts of good in actually limiting what our server attack surface is. It's what's driven attackers to the clients. The model is you bounce off a lured browser, say lured just viewing an ad on a web page, and the attacker on the outside bounces off the browser and hits internal corporate resources. So we've got a couple of different levels of access that we can get. Our first level is browser only. There's one iframe out in Europe and the other's down the hall. They have the same name, so they can script against each other. What do you get out of this by just using the browser, no plugins? Well, you get arbitrary HTTP. Now that's all, just website access. There's no important websites on any corporate intranets. Next level up is web plugins, is where you start getting in MS-XML, your generic XML HTTP request methods, maybe some of the stuff from Silverlight. Here you actually start getting not just HTTP, but some of the headers that you might want to use to interact with web services. Now, what are web services? RPC in drag. So, I think I'm kidding. No, seriously, so, you've had a lot of the internal resources have moved from servers, Corvo, RPC, that are difficult to manage, and have actually been we'll just do it all in XML and all will be well. It turns out that it's actually dramatically reduced the parsing load, and so things are a lot easier. The problem is they're so much easier, they put in so much more crap, because it's so easy to put in just one more schema element. So yeah, it's web services are a big old mess. And with the web plugins, you now get to bounce across into the corporate network and play with the internal web services. The final level of access are the sockets, and that's where I'm going to spend most of my time because I don't want to be limited to anything. I just want to bounce off your web browser and get to your file servers. Speak MySQL, speak SQL Server, speak SMB, speak RPC, speak NTP, whatever the heck I happen to feel like. It turns out Flash will give you arbitrary TCP access. In Java, TCP, and we'll throw in some UDP as well. Let's talk about what plugins are actually giving us. Java. This is a very instructive example because Java was the original target of the 1996 Princeton attack. From what they did after realizing, wow, it's 1996, but security actually exists. They did the right thing. They totally locked down the applet interface and made it so that the applet had to download the content itself, and because the applet downloaded the instructions, it knew what IP address it came from, and because it knew what IP address it came from, it would only attach the right IP to the right content. Great. The problem is that there was a totally separate way you can instantiate Java objects. So they put in this big, great wall that has stood for 11 years, and they put a little door over here. You just walk around. It's called Live Connect. It does not work in Internet Explorer. Who knows if that's intentional? But it does work in Firefox and Safari, though. And, it's totally rebindable. You just get to start up a Java object from within JavaScript, and Java has no idea where that JavaScript came from. It just gets a blob. Hey, can you open a socket? Okay, thanks, bye. Yeah, they're screwed. So, but it doesn't work in Internet Explorer. What does work in Internet Explorer is Flash. And this is sad. They tried so hard. Probably the most work going on in the industry right now to do cross-site scripting stuff securely. The people who are actually thinking hardest about how to actually do these complex security models, Adobe's doing a really, really good job of this. And they built this entire huge framework for XML documents that describe security policies. And unfortunately, that XML stuff is also vulnerable to DNS rebinding as well. So you get around the security policy by using the same thing. The effect sucks. You get arbitrary TCP access. You have to do some tricks to get below port 1024, as if that meant anything anymore. Who in this room thinks ports below 1024 is at all a security use at all? Okay, so here's the deal. Traditionally, the idea was, okay, users will use servers on ports above 1024. Administrators below 1024. Now you'll be able to differentiate a user-started service from a system-started service. This seemed like a great idea at the time. And then you look at ports like, RDP above 1024, MySQL above 1024, SQL Server above 1024. Turns out there's a crap ton of really useful stuff that's above port 1024. So it's a kind of a useful security mechanism now. So, mechanisms for rebinding address. How do you actually get Flash to see motion from, okay, download this movie from this address, get this security policy from this address, but now, only now should you go ahead and go over there. How are we going to do that? Alright, we got 3 ways. First way is what's been commonly known, the other 2 I'm bringing to the table. So, the first way is called temporal modulation. When you get a record back from DNS, it's got a time to live. It says, this value you should hold on to for this many seconds. And that value could be 0. And what happens is it says, oh, okay, the first time you look it up, you get an address. The second time you look it up, don't cache it, it might have changed, get an address. Third time, don't cache it, it still might have changed, go look it up. This happens to be the exact functionality that we want to abuse. We want you to look it up at time A and go to the server in Europe, and time B and go to the printer down the hall. So we'll just use it for what it's meant for. And so you get these networks, they brag, oh, we've solved this problem for years. We say records have to last at least 5 minutes. Because hackers just can't wait 5 minutes to break into your network. But alright, you want to play that game, and turns out we got 2 more. Guess what else you can do in DNS? You can return 2 records at the same time. Yeah, so basically when you look up bar.com, it returns both the address out in Europe and the address of the printer down the hall. Now there's a bit of a problem. What if the browser picks wrong? You know, sometimes you want it to go to one address, sometimes you want it to go to the other. What if the browser guesses incorrectly? Well, I've got this really crazy, awesome hack. It's called trying again. Amazing how well that works. And I'm not going to go too hard into how the trying again works, but here's a big messy slide that tells you how to try again. So, people are trying to use DNS TTL as security technology. They were never designed to be a security technology. Things always die when you decide to turn one into them. Finally, we have something less a security technology than virtual machines. So I used to call this Tommy the Tank Engine security. I think it's safe, I think it's safe, I think It turns out that's the wrong tank engine that says that. No, it's actually, and I'm not joking, the pony engine that says that. Wow. So it turns out overriding a TTL when you actually own the record at play is trivial. It's by design. Here's how you do it. So, when you look something up in DNS, you do not necessarily get back an address directly. Oh no. You can get something called a CNAME. That says, I know you looked up bar, but bar's just an alias, man. That's actually 2.bar. And here's 2.bar's new address. It turns out this, and here's its new address, actually overrides whatever was in the cache, regardless of TTLs. Works like everywhere. So here's what it actually looks like. We're going to look up one.foo.notmallory.com, because you know the server's totally not Mallory, it's totally not malicious out to hack you. You can tell because it says it's not Mallory. Right, so we're going to look up one.foo.notmallory.com. And it's going to reply and it's going to say, nah, you didn't mean one.foo. You meant bar.foo.notmallory.com, and here's its address. And indeed, when you check the cache, you'll say, okay, bar.foo.notmallory.com, 9 seconds ago, 120 minus 111, 9, I can do arithmetic. Bar.foo is going to go to 10.000. Sweet! This should be valid for another 111 seconds. Unless we look up 2.foo.notmallory.com. And it as well is going to say, no, you meant bar.foo. But here's bar.foo's new address, just so you know. Now, when we look it up, oh, look, it has immediately rebound to a new address. Sweet. I hope you enjoyed that 5-minute limitation of yours, because it totally broke. So, review. By swapping addresses out from underneath the web browser, we can get arbitrary TCP and sometimes even UDP access to hosts reachable by the client. What can we do with this? Hell. Can we VPN into corporate networks using nothing but a lowered web browser? Sure, it's easy. Okay, it's a total pain in the ass. It takes like 7 programming languages and 6 protocols. What is it with the web designers out there? Every time you blink, you're in a new programming language. Totally easy. Alright, we got 3 actors in this little dance. We got a browser. Browser's got access to internal resources. We got an attacker. The attacker wants access to these internal resources. And then we got the proxy. And the proxy is going to hook the browser up to the attacker. And the software written to do this, and the name will make sense in a while, is called Slurpee. Slurpee is a multi-point protocol server built using the Perl object environment. Very nice, non-blocking, supports one server with lots and lots of different protocols that it handles. And it turns out what we need to do, the attacker is going to give us TCP streams that need to be sent off through the browser. The browser is going to pull down these TCP streams over HTTP. Remember, so the deal is that the browser is like a network stack that you get to give code to. This is awesome. Slurpee's got to handle DNS. All those crazy DNS tricks, yeah, Bind ain't doing that. So we need to have a Slurpee run DNS. And because there's some security policy stuff that Flash handles, called an XML socket, we got to put in a server for that too. That wasn't a big deal. The basic theme is the attacker connects to the proxy, which manages the appropriate resources in the browser to service the attacker's connections. Now, what we do is we build what I call a bucket of sockets. The browser connects. It establishes an iframe called a bucket. The bucket polls for new connections to establish. And usually there'll be nothing there. But you know, eventually, eventually the attacker's going to have something he wants. And be like, I want to go to 10.0.1 port 80. And the attacker's going to register with the proxy and say, hey, give me access to this. Browser is going to come to the proxy and say, hey, you got anything for me? Proxy's like, yeah, I got something for you. Give me a connection to 10.0.180. Now the browser spins up a second level iframe. It is stored in this original iframe is the bucket. And each of the child iframes in there, that is the socket. It's like a socket, but it sucks. Now, the bucket comes from, whatever site, bucket.malware.com. But each of these sockets comes from a dynamically addressed site, address. In this case, say 10.0.1foo.proxydomain.com. Now that doesn't mean it resolves to 10.0.1 yet. It just will at some point in the future. This second level iframe is called a socket. You're going to note, by the way, this is a very obtuse design. It's obtuse intentionally. People have proposed some really bad ideas for solving this problem. Like ideas that laughably don't work. I've just silently made all those bad ideas fail in this design. So, what does it actually look like? Anyone hear about JSON in this place? JSON is like XML, but significantly less hideous. JSON is basically, you get the same results of XML, but you just evaluate it in JavaScript or parse it in JavaScript, and it just works. You now have this huge, this would probably be like 5 slides in XML. Very small in JSON. But what it looks like is that the proxy is going to say to the attacker, hi, you have a connection, you're going to have a set of connections to 10.0.1. Connection 3 in there, it's going to have some sequence numbers, some acknowledgement numbers, some data to the browser, some browser state, some server state. Okay, fine, I ported TCP to JavaScript. What? Saturday night. So, the ultimate question, how many DNS requests does it take to get to the center of your corporate network? Well, we can't use JavaScript alone. The proxy can cause the browser to open up a socket, and the socket's an iframe. But what's going to happen in there? Well, JavaScript can't do it. We need to get a Flash object. We need to basically drive the Flash object with JavaScript. Now, there is some way to do this right in Flash somehow, but it turns out there's a really cool language out there called Hax. It's called Hax. I have to use it. It's a meta language. You can compile it down to Flash and JavaScript, and you can actually use Hax objects compiled to JavaScript from JavaScript, and the Hax objects can call their Flash equivalents. So Hax is actually a fantastic bridge between Flash and JavaScript. So I ended up writing all my stuff to it. So what I do is I compile a Flash movie. First off, the browser has to load the movie. And that's going to be loaded from 10.0.1foo.proxyhost.com, which is going to DNS resolve to the proxy's IP. Now, the first thing this Flash movie is going to do is going to say, I need a security policy that says I can do whatever the hell I want. And it is going to download that security policy, still same domain, from 10.0.1foo.proxyhost.com. Still, same IP, everything is great. But we're going to make a TCP connection. And we don't want that to go to the proxy's IP. No, we want that to go to 10.0.1. So what do? We go ahead and we send an HTTP message to the proxy. And we say, hey, dude, next time you get a DNS request for 10.0.1, I want you to mess with it. And will you believe it? You totally will. The next time when we actually do a connect call to 10.0.1foo.proxyhost.com, we do a third DNS lookup, and that server replies, oh yeah! That's at 10.0.1. And then you win. At that point, you basically have a connection, you just gotta manage data flows. This should not have been as tricky as it actually turned out to be. It turns out that when you have iframes, each iframe has its own JavaScript interpreter. They are running just like threads. Oh yes, I had concurrency bugs in my browser. Oh dear. Yeah, so the whole browser as an operating system thing, yes, browser making me want to bang my head against the wall with Python bugs. Yes. Like, why am I dropping 1 out of 50 messages? Oh, because it hasn't yet completed that list. So, what do we do for the data flows? Data is going to be received by Flash. Flash isn't going to do anything with it but send it back into JavaScript for management. So it's going to go down into the browser DOM of the second level socket. What's going to happen is the bucket is going to visit each of its sockets. It's going to say, have you got any data for me? Have you got any data for me? Have you got any data for me? The bucket is going to aggregate all the updates from all the sockets, is going to send them in a huge batch in an HTTP update over to the proxy. The proxy is going to decapsulate this batch of updates, is going to hand them to the attacker. The attacker is going to be like, sweet, I got an incoming SSH connection. Here, let me start negotiating with that. It's going to create a TCP payload going back the other direction. That TCP payload is going to be received by a browser from the proxy. The payload is going to be sent back into each of the sockets, and the Flash object is going to pull the updates out and send it out each of the socket connections that have been set up. Like I said, totally trivial. Believe it or not, it actually works. I'm going to try to demo it, but I have to warn you guys, I have no idea. Oh my god, my net is actually working. I think I can even demo this for you guys. Alright, let's try this out. So we're going to go over to bucket, not Mallory food. So we're going to go over to this. Maybe. Oh, come on. I hate when live demos fail. And it was working so well, too. Oh, wait, hang on. You know what? It's Toorcon. I totally need to do the live demo here. Anyone else be like, nah, I don't need the live demo. No, you guys, you need to see the real deal. So I'm going to make this happen for you. Anyone got like Jeopardy music or anything? There we go. So let's try this. Try that. Oh yeah, we got bucket. So now, we're going to go ahead, find out an IP address. Okay, 66. So we're going to say, this is just a little weird interface that's been shown. So we're going to go, we're connecting to the proxy. We're telling it, please give me a connection to 66.240.226.139, port 22, protocol 6. Because hey, we might be supporting UDP someday. So we hit enter. Oh, look, we got a socket that opened up. It's opened up an alert for no reason. Oh wait, it's socketed, it's connected, and wait for it. Oh, look at that SSH login right there. That's right. Anywhere else I'd fail the demo here. Alright, what are domains? You might notice I had bucket.notmallory.com talking to 66 whatever.mallory.com. How come those two could talk? Well, it turns out, normally they couldn't because they're from different domains. But there's a little exception in the same origin policy. Two hosts, if they share the same parent domain, they can opt in to join that same parent domain. So foo.notmallory.com and bar.notmallory.com can say, we both trust Mallory. Let us talk to each other. That's right, I'm using the same origin policy to pwn the same origin policy. So that's it, a little bit of housekeeping. That's a TCP and JavaScript implementation. But what about the attacker? How is the attacker supposed to interact with all of this? The attacker can go ahead and type NC, 127.01, 123.45. Oh no, I got much more fun ideas. So, was there anyone here who was in my original talk 7 years ago about Slurp? Okay, check this out. Back in the day, I think it was 2000 or 2001, I gave a talk on really, really evil things you could do with SSH. And one of the things that you could do is you could run PPTP, the VPN protocol, over SSH. Yeah, so I was actually using Slurp to do this. Slurp was old school when I gave the talk 7 years ago. Now it's being dug up from the grave. You actually can't find this code on the internet right now. I had to pull out an old hard drive. Dear God. So, Slurp is fantastic. It is basically 1995 called They Want Their NAT Back. The idea was is that all you had was a shell connection, a text interface to the internet, but there was this awesome new stuff, Mosaic. Not even Netscape yet, Mosaic. And you didn't have Win95. No, it was all about the trumpet WinSock in the house. And how were you going to get trumpet WinSock to talk to your shell account so you can Mosaic to see some porn? How are you going to do that? Well, thus Slurp shows up and basically says, all right, I got an account here. It lets me open sockets. I got a client here. It gives me a stream of packets. I'm going to parse the stream of packets, and I am going to create a series of socket connections. Creating a series of socket connections. This sounds familiar. So, there was a Linux PPTP daemon called PopTop, still around. PPTP, for the love of God, don't learn it. It's the most hideous thing on the planet. But you can think of it as, it takes all the streams coming out of your box, they get turned to packets, it takes these packets, encapsulates them, sends it to that guy over there. Just imagine, here's a stream of packets containing all your outbound TCP connections, and UDP even as well. So what you would do back in the day was you would use PopTop, VPN in, connect to Slurp, and Slurp was actually completely external. The entire PPP side was external. So with the SSH era, what I would do was, instead of running Slurp locally, I'd SSH 5,000 miles away and run Slurp over there. And now instead of VPNing into, the machine over in my room, I'd VPN to, some machine 5,000 miles away. Works really well. Well, Slurp was designed to handle its socket connections directly. You would tell it, please open a socket to 1.2.3.4, and it would do it all by itself. Well, what if we had a browser that was willing to open socket connections for us? Could we use Slurp to turn the packets back into streams and then pass those packets out to IE? Could we connect Slurp to IE? Why, yes, and that's why the software is called Slurpy. So, the general idea, the attacker's running an application that uses sockets. The sockets get their traffic sent over PPTP to Slurp. Slurp provides a set of streams to the proxy. The proxy tells the browser's bucket, open me some sockets. The browser opens the sockets, which provides some sockets. The proxy mediates the traffic between the attacker sockets and the browser sockets, and it all just works. You don't need to write some SQL client in JavaScript. No, you can just use SQL Explorer. You want to run Nessus over IE? You got Nessie. You want to run World of Warcraft over IE? You got WoWie. Any TCP-based protocol will just work. And if you want to mess with Firefox or Safari, you get UDP too. Impacts. Well, corporate firewalls are bypassable via alert browsers. Your home routers are at exceedingly high risk. For the love of God, go home, change the default password on those things. We had a whole era of attacks of people blindly attacking the home routers with cross-site request forgery. People are like, what you need to do is you need to make it so that the browser needs to be able to read your response. Right now they're blind. They're just sending stuff in. You need to make the browser find a cookie and repeat it back to you. Well, now, with this attack, the browser totally sees the cookie. Your home routers are not in good shape, and neither, I guess, are your corporate routers if they have web interfaces. Every browser is a proxy. There are lists out there that you can buy that contain all the proxies in the world. I mean, there's not that many, and then you just decide not to trust them. Now, you don't need proxy servers. You don't need a botnet to bounce off of. Every browser is a spammer. Every browser can send SMTP. Every browser can go ahead and do click fraud. Every browser can link to your instant messenger server. Every browser can proxy click fraud. This sucks. $1 billion was lost by Google to click fraud. The idea is that, there are sites out there that will pay an immense amount of money for a click. Like, you got a click for some disease that they're kind of sort of suing the pharmaceutical company over. You get a click from someone who might actually join a class action. It's like $10. So people will just create fake identities. Now these fake identities have been tracked by looking at the IP addresses. But now any browser can be used to be these fake identities. It sucks. So there are a bunch of other attacks possible. Stealth Tor, you can just be kind of sort of silently joined to the Tor network. Do stuff to protect neutrality. There's some peer-to-peer networking issues. Java's giving us UDP. UDP is symmetrical. You can actually have an entire cloud, a peer-to-peer cloud of browsers that are talking to each other, no servers involved, and there's no special code that gets deployed on the client. There's just Java. There's a little bit more. This was a joke. In fact, IP over spam was not just a joke, I was smashed. I'm over at DEF CON doing the TCP/IP drinking game, and I am asked the question, how would you get around the Great Firewall of China? Now, the right answer to this question was, go ahead, drop all the reset packets, ignore the firewall trying to shut you down. See also how to get around Comcast. How are we in a situation where China and Comcast are doing the same thing? Dear God! But you see, I'm smashed. And so I'm like, no. China sends a crap ton of spam. China receives a crap ton of spam. Let's go ahead and encapsulate all of our IP traffic in Viagra spam. It's perfect. It's high bandwidth. It's low latency. There's tons of masking noise. You've got like 50,000 other servers that are making you invisible. This is perfect. And people laugh, and I laugh. They would never actually think of building this. And then I look at this hack. I'm like, well, I kind of have IP inbound, and I kind of have the ability to send spam outbound. Dear God, I was joking. All right, so can we fix this problem? So check it out. Flash, I've talked to some of the Adobe guys. They're going to fix the worst of their issues. Arbitrary TCP from Flash is going to go away. In fact, actually, just to clarify, Flash does not have arbitrary UDP. That's an error on the slide. Java, I have not heard a word from Sun. I'm not saying that maybe I should or shouldn't have. I'm just saying I don't know what Sun's up to, but you know what? They don't work in IE. Browsers themselves, where you use an iframe or you use MSXML or you use any of these other things, yeah, we're probably doomed. I don't want to be doomed, but we're probably doomed. First off, we have to detect that there's a cross-IP script. Remember, cross-IP scripts are legitimate though. Google does it all the time. Yahoo does it all the time. If you break it, you break the web. Funny thing in security, you're not allowed to break the web. People have tried. So, let's say you actually detect that there's a cross-IP script going on. What do? Well, people are using this stuff. Theoretically, you could have Google and Yahoo and CNN and all these sites opt their addresses into some sort of, yes, this address is part of the Google land, this address is part of Yahoo land, this is great. But how do we enforce that? When can we say so many people have gone ahead and shifted over that we can go ahead and make the browsers enforce it? You know what, that's like a 4-year thing, 5-year thing, maybe. So, yeah, even if we could snap our fingers and say, there are highly motivated server providers that want to shift over, we still have all these old browsers that are just going to need to continue to be supported. It sucks. And all those old browsers are going to be vulnerable. So here are the mitigations that people talk about. One that they talk about a lot is host header checking. The idea is same origin policy was indeed broken from the start, they screwed up, and they can't fix it in the client. So what they'll try is, alright, we screwed up the client, let's have the servers we care about change the way that they operate. Turns out that legitimate clients will put in a host header that declares the name of the site that they were going to, that they thought they were going to. So if bar.com has a DNS rebind to, google.com, Google will actually see bar.com in the host header. And then they might know that there was an issue and they could refuse to serve any content and so on. So in other words, the few sites that if you don't want to get hacked, make this change. This is not how security normally works. It's not how it actually works at all. But it will actually stop the worst of the issue, which is click fraud. The servers that actually receive clicks can be configured to go ahead, take a look, and see, okay, this host header was wrong. This did not come from content that I hosted. So you can do that. Where it massively fails are devices. Your printer does not know its host name. Therefore, it cannot reject, maybe my name is bar.com. It doesn't know. So the other thing that people have been talking about has been doing something to deal with external to internal routing. This has been going, I've heard this from like 3 or 4 different sources. Why is it that a site on the internet can refer to your router inside? And you know what? There's an argument there. I don't know what's going to happen with that. But it does kind of handle internal devices. When I say sort of, I mean you sometimes don't know what an internal device is. You don't. So here's what's weird about firewalls. There are 3 security domains. There's your LAN. You can tell something's on your LAN because it didn't come from your router. There's the internet. There's your corp net, or your local net, or your behind the firewall net. You don't know where the firewall is. The firewall doesn't tell you this packet came through the firewall. You basically assume if the packet reached you, your firewall was okay with it. Either it came from the internet or didn't pass the firewall. One of the two. That's about all you know. So the problem is that saying, we're going to have an external to internal routing check, you don't know when you get a link somewhere that it's actually going out to a foreign network. It could just be going to the dorm 3 buildings away. You have no real way of knowing. And that sort of sucks. So ultimately, at the end of the day, we can half-ass fix some servers, we can half-ass fix some clients. But the browser, as a generic router, is probably going to live forever. I'm a little sad about that. So, have fun. So, one thing we can do, though, is let me see. Anyone got a time check for me so I know what time it is?
24 after.
24 after, okay. We'll go a few minutes over, but not 2. Some of this stuff has uses other than breaking into networks. Who knew? When I started talking about network neutrality last year, I came up with a hack that actually worked. But it kind of involved flooding a link with so much traffic that it started dropping packets. It turns out you can't release code that involves taking down chunks of the internet. Even I can't. So I actually spent the last year thinking, well, what else can I do to possibly find out that someone... First of all, we need to stop talking about network neutrality. Network neutrality is the status quo. You don't beg for the status quo. What we're talking about is whether provider hostility is allowed. In other words, let me define provider hostility for you. If you're sniffing my traffic, you're probably hostile. If you're altering my traffic, oh, you're definitely hostile. If you're censoring my traffic, if you're selling my traffic to choice point, you're very, very hostile. Here's a very simple metric. If the US Army would shoot you in the head for doing it, you're probably hostile. I'm just saying. So, what do we need in order to detect provider hostility? First of all, there are 2 kinds of ways that a provider can be hostile to you. First, they can send your traffic at different speeds. So in other words, this kind of traffic is going to our internal voice over IP provider, fast. This kind of traffic is going to Vonage, 1 second delay. Things like that. The other kind is content injection, where you actually find out that they're actually changing things in the middle. Now, here's the issue. The internet is big. And there are lots and lots of hops, and at different speed, and even different content can happen from all sorts of different locations. How do you find out that your last mile, that your ISP is actually being hostile to you? Well, what you need is to know, given identical network paths for 2 websites, is the last mile provider hostile to content from one site versus content from another? Well, how do we know that they even should be looking for anything at all? Well, anyone who knows anyone who's working in the router space knows the carriers are basically demanding this. These are the features that are being built into the next generation of routers. The ability to change stuff, to slow it down, to inspect the crap, to read your email. Like seriously, these are the features that your ISPs are trying to buy. This is the decisions that they're making. There are repeated news articles about ISPs even going so far as to replace ads, and companies setting themselves as ad replacers. This is interesting. I want to Anyone here know about this Times Square effect? When you see Times Square in a movie, guys, that ain't Times Square. Even if it's not computer generated as a movie, all the ads have been replaced because there's no contractual obligation from the movie maker to show what was physically on site. Well, there's no contractual obligation between Comcast and Google to actually show the ads that Google put there. No contractual relation between Comcast and Yahoo to show the original ads. And you know, Comcast is taking a look and they're realizing that, well, I don't want to say Comcast specifically, all the ISPs are taking a look because they're saying, you know, all the money's going to the ads, we're hosting the ads, going over our pipes, where's our cut? They finally figured out, man-in-the-middle attacks are awesome. They are the man in the middle. Let's go make some money. Exactly. And the deal is, users don't care. Users tolerate ads. They don't mind that much. Let me tell you, you know how much you could make if you could say, I will make you the top link on Google on 10 million desktops? You will make money. Because Google won't sell that top link. You want that top link, you gotta be good. And it's a lot easier to pay Comcast than be good. Comcast and AT&T. I don't want to pick on Comcast. They did some responsible things lately. So, one thing you can do, actually, it turns out, some consumer networks have transparent proxies. What this means is they take all traffic outbound in port 80 and coalesce them into a single proxy instance. And that uses the host header to route requests to the correct destination. Well, check this out. We have, with Flash, the ability to make a TCP connection wherever we like. Now, we've been using rebinding to move it, but eventually that's going to go away, and it's only going to go to one IP address. So, the ioactive.com IP address is the only one I'll be able to make a direct connection to. But if you're behind one of these transparent proxies, guess what happens if you ask the ioactive IP address for Google's content? Well, the packet goes off to the last mile, says, oh wait, this is port 80, redirects to the transparent proxy. Transparent proxy says, well, apparently you wanted Google. Here's Google's content. So now, because of the transparent proxy, you can go ahead and retrieve content from other sites. Beyond being an awesome attack, though, here's where things get really fun. You can tell, I download from the proxy stuff from Google and it comes at one speed, and I download from MySpace and it comes from another speed. And you're always getting stuff from the transparent proxies. So you can actually specifically extract last mile specific data because all websites are hosted out of the same proxy. How awesome is that? Now, we can get even more fun. There's something called silent sensors. And silent sensors basically say, you know, we can't put in a transparent proxy because these things are horribly unstable. This is true. But what we can do is we can put in a device that silently slows down sections because the host header was something we didn't want. Well, with Flash, we can set a host header. You can go to IOActive and you can request, give me MySpace, give me CNN, give me Yahoo. And that request is indeed going to go to MySpace, CNN, Yahoo. But the provider infrastructure is going to be like, wow, Yahoo got a new IP address. It's over at this new one, the IOActive address. And then they'll go start messing with IOActive. Or mess with, you know, they actually think they're messing with Yahoo, CNN, whatever. So you can go ahead and basically put in arbitrary host headers to elucidate what the policies are. Now, here's the issue. All of these stunts are totally detectable. I assume there's some guy just like me who goes like, oh, I can totally mess with Kaminsky. So I had an interesting question. Could I create a network neutrality violation detector? Could I detect provider hostility so well, even I couldn't selectively turn off the hostility when I was looking? See, either way I win. Either I beat myself or I can't beat myself, so it's awesome. And it turns out I won. What do we want to do, right? This is going to go like 3 or 4 minutes over, hopefully. We want to spoof sites on the internet, right? We want to know what these sites would see. We want to be able to respond as if we were these sites. We don't want the real sites to get in our way as we're impersonating them. Okay, good luck. I mean, look, You can know IP spoofing all day, but in order to inject into a TCP stream, you gotta know the sequence numbers. You gotta know these random values between 0 and 4 billion, and if you don't guess it, your traffic's getting dropped. And clearly there is no way you could ever get a browser to tell us the sequence numbers involved in its transactions. Oh, hell no. Oh, wait. No, I think that's a hell yes. I mentioned this to one of my friends. He Googles, he's like, hey, Dan, it's called Packet X. You install this ActiveX control, it sniffs traffic. Oh, sweet. Now, we can have some fun. Because now, look, what normally stops Mallory from pretending to be a random site on the net, Mallory doesn't know the sequence number. Now we can get the sequence numbers tunneled. And now, our Mallory can go ahead and spoof traffic from MySpace, CNN, Yahoo, wherever Mallory feels like it's awesome. Now there's a problem. Remember I said that we don't want the real site to mess with us? If our client, if Alice responds to Mallory and says, oh great, you sent me some data, the real site's like, what the hell was that? I didn't send you anything. Abort, abort, go away. Unless we tell the real site to screw off. So it turns out, when we get the sequence numbers, we actually find out what the precise sequence number would be to tell the legitimate server, no, you go away now. So what happens is we decide we want to go inject on MySpace. We tell MySpace, here's a reset, go away. We'll take it from here. Now, by specification, what's supposed to happen is that, remember, all these acknowledgments are being used. We're sending all this traffic to Alice. Alice is acknowledging to MySpace. And, you know, MySpace would normally receive all these acknowledgments, would normally say, dude, I'm not talking to you, bye, and send some resets. But we have these great things, they're called firewalls. They're all paranoid. Firewall's like, I don't have a session with you, clearly you're a hacker, I'm gonna pretend you don't exist. And so it drops all your traffic, thus totally allowing Mallory to go ahead and spoof all this site. It's awesome. Remember, from the provider network, provider just sees all this traffic getting sent from quote-unquote MySpace, getting acknowledged to quote-unquote MySpace. It's perfect. The only people that know that what is happening is the client and the server, Alice and Mallory, are collaborating to mess with the provider that may potentially be hostile. Now, of course, you know, Alice is acknowledging traffic. Alice needs some way to get that traffic to Mallory. Clearly, the normal ACK stream doesn't work, but, you know, we have a sniffer. So we just sniff all the acknowledgments, tunnel them in AJAX using this stuff from earlier, and it just works fine. So yes, we're actually going to move TCP over HTTP. Rock. So, why am I so obsessed with actually doing this? Check this creepy stuff out, you know. The goal is to identify the applications being used on the network, but some of these devices can go much further. A company like Naris can look inside IP addresses, pick out HTTP, can reassemble emails as they are typed out by the user. My God, they can't even wait for you to hit send to be creepy. So guess what I can do to these guys now? I can impersonate anyone who doesn't hack my traffic. I can generate arbitrary traffic that appears to come from anyone I want, and I can provide deep packet inspectors with a whole bunch of fun stuff to inspect. So, don't mess with my traffic. It's not a good idea. Conclusions. DNS rebinding threatens the boundaries of your network. There are multiple rebinding mechanisms and many major use cases for each of them. This is gonna suck to fix. The web really needs to have some work on its underlying security models. It's great for public to public, it's not so great for private stuff. We may need to consider doing something to imply integrity. One of the things I didn't mention, because of ad replacement, every site's going SSL within 18 months. Not every site knows it yet, but I'd invest in SSL accelerators. And there are mechanisms for detecting provider hostility, and I'm building them. That's it. Okay. So go ahead. So I'm looking for 1 or 2 questions and/or beer, and I have comic books if it's a good question. Any questions? Question was, is V6 going to fix this? Like many things, V6 is totally orthogonal to this problem. You can totally rebind to another IPv6 address just like you can rebind to another IPv4 address. V6 does not help, nor does IPsec, nor does pretty much anything at layer 3. Go ahead.
So with regards to sites being or companies being able to say, hey, you know, I am doing these DNS rebinding tricks or DNS-based distribution. How does the security aspects of that interplay with CDNs that host multiple sites like Akamai or simple like hosting providers?
So the question, actually a good question. Here, grab a comic book. The question is how does the legitimate use of Google, Google will spread its content across a lot of IP addresses. How does this scale to Akamai, which is actually spread across not just lots of IP addresses, but lots of sites? And this is, oh wow. That's fantastic. Fantastic. No, so this is, take 2 books, this is great. So one of the proposed solutions is that, all right, we're going to have servers recognize the legitimate host headers, and they'll only respond to them. Well, guess what? You have Akamai that's responding to host headers from like 1,000 different companies, and any of them get to mess with any of the other ones. That is awesome and totally unrealized, and we're having a beer after. Any other questions? All right, guys, track me down later. All is awesome.
Yeah, real quick before you guys all head out the door, we got lunch starting here for an hour and a half. See you back at 2. But in the meantime, in the vendor area, we've got a handful of vendors there, including someone that's selling these RFID wallets. They're really nice. They're all handmade, made from recyclable materials. Check them out.
Ask Kevin Polson about DES, okay? And Nick's over there laughing about that. He knows what I'm talking about. Use Google. I'm not saying actually go ask Polson about it, but use Google. We'll find out what I'm talking about. But DES has some problems, and it can be used against you. Ask former spoofs about PGP, GPG, okay? Because there's the rumors that go back and forth. You have some people say, oh, it's crackable, oh, it's not, oh, it's backdoored. I don't think it's backdoored. I really think it's probably in the way that it's been implemented in some form or fashion. More than likely, if you do something really scary or creepy and you GPG encrypted, if they do get a hold of that and they do manage to do some type